Hi everyone. So today I'm going to show you how to write your first Bayesian logistic regression model using a STAN program. So in this video I have assumed that you have already installed your STAN interface into your RStudio. So after you have installed STAN interface into your RStudio, then if you open a new file using this option, you will see this STAN file option over here. So if you open that, now you can see the basic outline of a STAN program. So after you open your STAN file like this, you will see three main sections in this file. So these sections are basically the main sections in a basic STAN program. This first section we call it as the data section. In this data section we will define the dimensions of our input to the model. So that means let's say that we are going to fit a logistic regression model. In this case we have to specify the dimensions of our response vector and also the dimensions of our predictor matrix. And in the next section, which is called as these parameters, we are going to define the dimensions of our parameters that we are going to estimate. And the last section, which is the most important section in our model, in this section we are going to define our prior distributions for our parameters and also the distribution of our response variable. So let's edit this code in order to run a logistic regression model. So in this STAN programming language, when you define the variables, unlike in R, you need to type the variable type also. So that means if it is an integer, then you need to type the variable type as int. If it is a real number, then you have to type it as real. If it is a vector, then you have to define it like this, so on. So as the first data input in our model, we need to specify the number of observations. So I'm going to define this number of observations in my data as n, where this n is an integer, and also I have given a constraint to this number of observations so that it is always a positive integer. So in order to define it as a positive integer, you need to specify this constraint lower equals 0 like this. Then I am going to specify the number of predictors. So the number of predictors is always greater than or equal to 1. So the lower limit should equals to 1, and I'm going to name my number of predictors as this. So this is number of observations, and this is number of predictors. The next step is to define the data matrix. So since it is a matrix, the data type should be matrix, and after that inside these square brackets you need to define the dimensions of your data matrix. So in this model, one thing I need to mention is that I'm going to define my intercept as a separate parameter. Because of that, in my data I will not include this intercept as a one of the columns. So because of that, my dimensions of my data matrix is the n times number of predictors. So I'm going to name my data matrix as X, and the next one is to define my response vector. So in this case I'm going to define my response vector as an array. So if you write an array in this stand program, first you need to define the variable type of that array, whether it is an integer array or it is an real number array, so on. And then after you type the variable name, in front of that you need to define the dimensions of your array. So here my response vector should has the dimensions of n, where n is the number of observations. And since it is a binary vector, I'm going to define some constraints where lower is equals to 0 and upper is equals to 1. So this is how my data section will looks like. So now I'm going to define my parameters from my logistic regression model. So in this logistic regression model, I have only one type of parameters which we call as regression coefficients. So this alpha, I have defined this alpha as the intercept of my model. Where this intercept is a real numbered parameter, and this beta is my regression coefficients, where this regression coefficients is a vector where the dimensions of this vector will be equal to the number of predictors. So after you specify the parameters, now you can define the regression model. So in this model section, you need to specify the priors. You will specify the priors, then the likelihood or the likelihood or the distribution of y. So in these priors, you need to specify the priors for each and every parameter that you define. So for an example, for beta, I'm going to define a weakly informative prior, which is a which has a normal distribution with mean 0 and a standard deviation of 10. So in this stand program, unlike in the usual settings, the parameters of the normal distribution is mean and the standard deviation. Then for the intercept also, I'm going to define a weakly informative prior like previously. After that, I'm going to define the distribution of for the my response variable. So in this response variable is a binary response variable. So you can have some choices for this. Likewise, for an example, you can use this Bernoulli logit GLM as a response distribution, or this Bernoulli logit function. So all these methods will define the same thing but in different ways. So for this model, I'm going to use this Bernoulli logit GLM function. So if you use this, then if you use this Bernoulli logit GLM, first you need to specify the predictor matrix. So my predictor matrix is X, then put a comma there, and the next parameter is the intercept, where intercept is alpha, and the last parameter is the regression coefficients, where it is equals to beta. Alright, So this is the stand program that you can write to run a basic logistic regression model. So after you write your stand code, you can save this into your system using this save option. So now I have saved this stand code using this name, and if you have done any mistake in your stand code, it will shown to you using this symbol, this cross symbol. So here you can see that I have misspelled this vector. So if you correct this, it will automatically remove that cross symbol. So after that you have to save it again, and then you can compile this code to see whether you have done any mistakes. So if you got this message, that means this stand code has compiled without any error. Okay, so now after you have reshape your data so that it can input into your stand code, now I'm going to show you how to run this stand model. So to do that, first you need to import this rstand package into R, and after you import this rstand, you need to run these two lines also to run this model more efficiently. Then here, using this stand function, you can run your stand model. So with this file parameter, you need to give the location for your stand code, where that means the location that you saved your this stand code. So I have, since I am running in the same directory, because I have created a package here, so because of a project here, because of that I need to just give the name of the function, name of the file, which is logis underscore dot code dot stand, and the next, as your data parameter, you need to give the a list that you created earlier. That means this data underscore list. And next you can define the number of iterations, that means number of MCMC samples that you are going to generate. So let's say here I'm going to generate 1000 MCMC samples, and I'm going to run it for, let's say, only for 2 chains. So now everything is, I think, okay. So now you can run your first stand code like this. So this will take some time, so depending on your data, it will take like 1 to 3 minutes, depending on your the performance of your laptop, and depend on your data. So here, actually, if you wait for like 4 to 5 minutes, here if you run the same code that I have written here, then you might get an error like this. So because I have done a mistake here, so because in my data section here, this parameter for n should be the first parameter of the result that I am getting from this dimension function, not the second parameter. So I have corrected it, and now I'm going to rerun this one. So now you can see in this viewer section in your RStudio, you can see this model is running. So if you click this reset option, you can see that you can see how this model will run based on per chain and per iteration. So if you haven't done anything wrong, you will not see any warning messages here. This warning message, actually you can ignore that. That is mainly due to the some version mismatch in my RStudio. So if you don't see any warning message other than this, then that means you have run this code without any problem. So the next thing is to get the summary of the regression coefficients. So in order to get the summary of the regression coefficients, you can use the summary function, and inside the summary function you can give this the stand object that you fitted earlier, and if you want you can specify the parameters that you need to use, that you need to see. That means here I'm going to see the results for my intercept and my beta coefficients, and then if you run this one, yeah, here should be a comma. Now you can see the parameters values for each and every chain, for chain 1 and chain 2, and also as a summary, that means the average values based on both chains. Now you can see the mean parameter value for alpha is around -7.2, and for the regression coefficients it is around these values. And the things that you need to consider is this r hat value. If this r hat value is not close to 1.01, that means this model model has run very efficiently. And also you can see that this Bayesian regression coefficients you can get as this mean parameter values, and you can see that these mean parameter values will be very similar to this very similar to the results that you will get from the classical logistic regression model. So that means if you use this GLM function like this, and family equals binomial and data equals diabetes. Now you can see the regression coefficients for intercept is -7.18, and the Bayesian mean value is also close to that one. Here I have obtained it as -7.2, and for the other regression coefficients for BMI it is 0.08, and here also it is 0.08, and for the next one here 0.08, and for the next coefficient it is -0.007, and here it is -0.007. So likewise you can see that based on weekly informative priors you can get very similar results like in the classical method, but the main advantage in this Bayesian method is that you can get the posterior distribution. So using this posterior distribution you can quantify the variance or the uncertainty of this regression parameters, which you cannot do using this classical method. So in this video I have shown you how to write a basic code to write a logistic regression model. So you can modify this stand code based on your requirement, And in my next video I am going to show you how to extend this model so you can use a regularized shrinkage priors in this logistic regression model. So if you think this video is useful to you, please subscribe my YouTube channel. Thank you.